Hello, Rose. For 5.6, let's solve a couple of quadratic trig equations, trying a couple of different strategies out. First one, let's try solving by isolation first. 2 times the sine of theta squared is equal to 1. We might want to start by writing the sine of theta squared as the square of the sine of theta, like that, just so that we're clear when the operation is undone. Because if we're taking the sine inverse here first, because we see it from the outside, then we're left with square theta, which makes absolutely no sense. Like I said, solving by isolation first, not too bad, as long as I have a deep understanding of quadratics and the fact that the square of a positive or a negative number will be positive. So that when I take the square root of both sides here, I get the sine of theta is plus or minus 1 over root 2. Oh, and this one said to the nearest hundredth, but I guess I don't need it to be to the nearest hundredth because I recognize this ratio. We have been using curves to help us solve, and I guess if I draw a curve of y equals the sine of theta right here and figure out when am I at positive 1 over root 2 or negative 1 over root 2, I can see 4 solutions. I think because of the symmetry in my outputs, I'm feeling symmetry in my inputs. I think all of these are going to have the same related acute angle. But again, all of this might be moot because I recognize the sine of theta as the ratio of y to r. So maybe I choose to use a sketch in standard position, especially since my period is unchanged and I don't have a phase shift. A nicer circle would have done a better job here. Let's pull out the old polar bear. And ruin our circle with a axes in the middle. Right, so if we have a radius of root 2 and we're looking at a y value of 1, I kind of recognize that as being in a right isosceles triangle. Now here's y being positive 1, and here's y being negative 1, and there are my 4 root 2, root 2, root 2, root 2, 1, 1, negative 1, negative 1. 4 principal angles that have a related acute angle, principal angles that have a related acute angle of pi by 4. So I guess I would say theta, I'm not sure I need to list them as theta 1, theta 2. Let's just list them old-fashioned style. Theta is pi by 2, pi by 4, 3 pi by 4, 5 pi by 4, or 7 pi by 4. Okay. It's nice to show calculations where numbers come from, but I feel like my sketch does the trick here as well. Okay. The other approach that I wanted to try here was as a difference of squares. The advantage to treating this as a difference of squares is that I wouldn't ever forget to do the plus minus, which we have a lot of experience with. As a difference of squares, you just need to convince yourself that 2 is a square of an irrational number. So your x method, or the factor theorem, isn't going to work great here because I listed all the integer factors of 2 and I don't find any pairings that work. One, I'm looking for an inner term of 0 and that's not working. But if I recognize it as a difference and 1 is a square and the sine of theta is a square, then perhaps I just ask myself what multiplied by itself would give me a 2. And that gets me a root 2. So I'm going to try a root 2 sine theta with a 1 and a root 2 sine theta with a 1, making sure I always write it's equal to 0 because this is an equation I'm working with. And for my product to be negative 1, my signs would have to be opposite, and that's what makes my interior term 0. So I have root 2 times sine theta, which is 2 sine theta squared, plus root 2 sine theta minus root 2 sine theta, that's 0 sine thetas, minus 1. From here, then I have roots when the square root of 2 times the sine of theta minus 1 is equal to 0, or when the square root of 2 times the sine of theta plus 1 is equal to 0. And that'll get me right back up to that line right there. So I'll let you continue from there. Okay, isolation works fine as long as you remember the plus minus when you need it. Solving by factoring is a little bit more flexible, so keep your eyes open for it. Another option that I teach my grade 10s to use, and I try to encourage my grade 11s to use it when their quadratic is in a specific form, is solving by completing the square. So let's just review a quadratic. Let's say I'm asking you to solve when is u squared minus 2u minus 1 equal to 0. So when you have a quadratic equation in standard form, and you can't seem to find an order or a grouping that gets it to factor, notice I see 1 and 1 getting me to -2, but only if both of those are negative, and that product would be positive. Usually students default to the quadratic formula. And the quadratic formula should work fine with trig expressions, but it is a little bit awkward sometimes too. It doesn't always give us the simplest solution. Students often write the wrong thing on the left-hand side of the quadratic formula. So yeah, solving by completing the square, what I want to do is build this into a perfect square. And right now I have a u squared, and for this to be a square, this minus 2u must be split evenly. So that must be a minus u, which means this has to be a u by u, and that has to be -1 and -1. So my perfect square is going to be u minus 1 all squared. That means that to complete my square, I have to add 1. That would complete the square. I think it's a shame how many students are taught to complete the square without drawing a square, without understanding that they are completing a square. So I will add 1 to this to complete that square. Now this is a complete square. Of course, I'm not allowed to just add 1, so I'll subtract 1, because the only thing I'm allowed to add without changing the value of the left-hand side is 0. So that's me adding 0. Then I factor this as a perfect square. Whoops, that's a u minus 1 squared, like I knew it was going to be from my diagram. And I might as well collect this -1 minus 1 down to -2 equals 0. And from here, I have the choice of solving by isolation, u minus 1 all squared equaling 2, u minus 1 equaling plus or minus the square root of 2, and u equaling 1 plus or minus the square root of 2. Or solving by factoring as a difference of squares. That looks like a u minus 1 minus the square root of 2. I'll even put those in curved brackets for you. You're welcome. Times a u minus 1 plus the square root of 2. Our grouping for differences of squares in, oh boy, lesson 2.2, maybe 2.1, should prepare us for this if we've mastered that skill. Okay. We have a trinomial, but we visualize it as a binomial. It's not really a trinomial because those are both constant terms, but it looks trinomial. When I check with distribution, I get u minus 1 all squared plus root 2u minus 1s minus root 2u minus 1s. That's 0 of whatever those things were. And then negative root 2 times positive root 2 is 2. Giving me, when I set this equal to 0, u is equal to 1 plus root 2. Or when I set this equal to 0, u is equal to 1 minus root 2. The same conclusion as before. Okay. Now, variable substitution is an option. If you're going to notice the equation that I give you is going to just have cosine of theta where u used to be. I think that variable substitution in this course right now is kind of like training wheels, that we should try to factor with cosine expressions. We practiced this at the start of Unit 5 with the factoring worksheet, the algebra trig factoring worksheet. The other thing about solving by completing the square that I want you to be mindful of is I understand that students don't like to complete the square, especially if they have a bad experience with it because they weren't taught well or they didn't learn well. Not sure whose fault it is. But if your equation is already been completed, then it does not make sense. It does not demonstrate a high level of understanding for students to expand this to get it to standard form to use the quadratic formula. Okay, so I don't expect you to solve by completing the square. I'm not going to tell you to solve by completing the square, but if your square has already been completed, please isolate or factor instead of expanding. It's very important when this exponent gets larger. We generally want to avoid expanding. Fine. I'll give you an example once we get started here. So let's say that we want to solve when is the cosine of theta squared equal to 2 times the cosine of theta plus 1 to the nearest hundredth over theta is an element of 0 to 2 pi. Right. So we have a quadratic trig equation. It's kind of in standard form. Most people would probably start by rearranging, writing it equal to 0. Now it's in standard form. We could use the quadratic formula. The quadratic formula would be the cosine of theta equals negative b plus or minus the square root of b squared minus 4ac all over 2a. This is the biggest problem, and I think we discussed it in class, that students aren't aware what they're supposed to write here. Okay? They think that theta is their independent variable, but the quadratic formula doesn't solve for theta. It doesn't always solve for x. Okay, it's your expression that is being squared. It's your base, I suppose. We don't need it, so let's avoid it. Let's try solving by completing the square. So here's a cosine of theta squared. Let's draw a square. I have a cosine of theta squared. And minus 2 cos thetas. There's 1, there's 2. It has to be symmetric, which means I need to add 1 to complete this square. I have to subtract 1 to maintain equilibrium. There's the original minus 1 right there. That will complete, or factor completely, to the cosine of theta minus 1, all squared. I'll collect that to minus 2. So imagine I give you the equation here. If you expand to use the quadratic formula, it would not demonstrate a high level of understanding of quadratics, which we did in grade 12, which we did in grade 11, which we did in grade 10. Okay, we can't just depend on expanding and using the quadratic formula. Let's try factoring. This is going to be the cosine of theta minus 1 minus root 2 times the cosine of theta minus 1 plus root 2 equals 0. Make sure you have an equal 0 on every line. Check with distribution. Cos theta minus 1 times cos theta minus 1 is cos theta minus 1 all squared. Plus root 2 cos theta minus 1 is minus root 2 cos theta minus 1 is 0 of those things. Minus root 2 times plus root 2 is plus 2. This gets me the cosine of theta is 1 plus root 2, or the cosine of theta is 1 minus root 2. Now, with these irrational numbers, predictions can be a little bit trickier. So, I don't know, the question does prompt me to use a calculator. I might want to grab one, get it ready. But I think that I can tell that the cosine of 1 plus the square root of 2 is definitely bigger than 1, which causes a problem for the cosine ratio, because the cosine ratio is never bigger than 1. So this factor right here causes no solutions. I guess it would be up here somewhere, wouldn't it? 1 minus the square root of 2. Well, the square root of 2 is bigger than 1, so 1 minus the square root of 2 is going to be a negative number. I guess it'd be down here somewhere. Maybe I don't need a calculator to approximate it. I'm going to need a calculator to find the angle. Anyways, there we go. So I could do 1 minus the square root of 2 and say, oh, it's about negative 0.414. Negative 0.4 is probably close enough. Right, I already have that number stored in my calculator. I will ask my calculator for one solution to that. My calculator tells me probably theta 1 right here. Number a little bit bigger than pi by 2. Yeah. Theta 1 is about 1 point, well, it actually rounds off to 2.00, I guess, to the nearest hundredth. And because of the symmetry of the cosine curve around its maxima, theta 2 is going to be about 2 pi minus 2, which is not pi. Let's just approximate it. 2 pi minus that answer that I just had is about 4.29. There you go. Right. Make sure you are strong with quadratic prerequisites. Make use of any material or extra help if you need to fill in some gaps from grade 10 or grade 11 or grade 12 quadratic work. and make sure that you try it out.